Hello and welcome everybody to the IAgrE Engineering for Food and Drink seminar on food extrusion. Our speakers today are Gordon Young and Dennis Forte, who are food engineering consultants from Australia, who are highly experienced in extrusion processing. They have been presenting industry training courses in extrusion and related areas for over 25 years, with annual courses in Norway, Switzerland, Chile and Thailand, as well as their homeland Australia. The presenters have also released a range of textbooks specifically directed at understanding the technical aspects of extrusion. Gordon will present an overview of extrusion in the food industry, showing the range of products produced by extrusion and how the process is changed to produce such a wide variety of product characteristics. Gordon graduated in agricultural engineering in 1980, later undertaking a Master of Engineering Science and graduate diploma in business. He started his professional career in research related to mechanical harvesting of fruit. He moved into the area of food processing when he became the first engineer at what was then the Queensland Food Research Laboratory, a state government institution in Australia. After spending some time managing the agricultural engineering section in the state government, he moved on to lecturing in food technology and engineering at the University of Queensland. It was during that time that he was introduced to extrusion technology. For the last 20 years, he has worked as a private consultant in food engineering, specializing in areas of thermal processing, drying, and extrusion. Dennis will then present an overview of alternative extruder configurations, the role of rheology, and will also discuss some of the key considerations for extrusion process setup. Dennis is a chemical engineer graduate of the RMIT. He has spent 10 years with the Mars Corporation. During this time, he was involved in process and product development roles with the areas of confectionery, canned pet food, and dry pet food extrusion. He then spent 5 years with the Uncle Toby's company, who manufactured breakfast cereals, snacks, and pasta, as the process engineering manager. His key areas of expertise include extrusion processing, mixing technology, process modeling, process optimization, and drying technology. He has been practicing as an independent engineering consultant since 2000. Just before our speakers start, you are all currently muted. If you would like to ask questions, please use the chat function at the bottom of your screen. And then at the end of the presentation, we'll unmute you so you can ask in person. So over to you, Gordon.
Thanks very much, Charlie. So I'll share my screen and we'll get underway. So as Charlie said, there's two of us. So I'm going to give you a bit of an overview of extrusion, especially if there's some of you who are not particularly familiar with the technology and what it's used for. And I'll talk a bit about how the ingredients are transformed into the products. Because of course, when we're processing foods, it's about cooking them properly. And that's a key part of this process. Dennis will then talk more about the actual equipment, extruders, and some of the processes that are used. And I'd like to thank Charlie and Sarah for the invitation to talk to you. As Charlie mentioned, I actually did graduate in agricultural engineering, so it's interesting to make this link back to my original profession, considering that in Australia, food processing isn't as well connected to agricultural engineering as it is in some other places. So I'll start with the overview of extrusion. And starting very basic, what is extrusion? And if we look at it just from the point of view of a dictionary definition, it's about a process in which a material is forced through some sort of restricting orifice or die. Now, that's a pretty simple definition, but in fact, it immediately brings up one aspect that is key to understanding the process. And that is that if you can force the material through a small hole, that means the product is capable of flowing, that it's acting like a liquid. And Dennis will talk more about that, but in extrusion, we put solid ingredients into the extruder. We produce solid products out the end. In between, it's going through a liquid, a melt phase. Now, extrusion's used in a lot of industries. So in plastics, for example, aluminium extrusions, a lot of you would be familiar with that. One difference when we apply this in the food and feed industries is that the materials are going through a whole range of irreversible changes. That is, they're being cooked. So I'll talk more about that soon. But one thing this means is that we can't just take the product from an extruder and put it back in again, because you can't cook an egg twice. So we've got to get the cooking process happening right, because that is a key aspect of the quality of the product that we're producing. So this process you'll often see referred to as extrusion cooking. The cooking part of it is central. Some reasons why we use extrusion. We can produce products with properties that aren't achievable by other alternative means. So, for example, some of the textures of extruded snacks, we can't really achieve quite the same way by any other method. We can make some unique shapes, can get a good control of the degree of cook, which is important in animal feeds. Another reason is that extrusion is an efficient process. Relatively high throughputs for less labour, reduced energy, reduced wastage, all those sorts of good things compared to traditional processes. But one thing we'd also note, and you'll see here some examples as we go through, it's often not really the same. Two products that you might see as the same, produced by extrusion and by other means, are fundamentally different. And we'll talk a bit about that during the presentations. Extrusion's also very versatile. So we can make a range of products. And so there's a few here, things like expanded snacks and what we call third generation snack pellets. So a lot of the snacks you might favour are extruded. A lot of breakfast cereals are extruded. There's things like pastas. Often we associate extrusion with making something of a particular shape, but some of the infant foods use extrusion as the cooker, and then they mill it into a powder. So if you have an instant infant porridge, for example, those are often cooked by extrusion. Some confectionaries extruded. And then things like textured vegetable proteins, meat alternatives are extruded. And even flavour compounds, another case where the extrusion is used essentially as a chemical reactor to produce flavours, and the product that comes out after it's produced is milled into a powder to be used in the industry as a flavour compound. And that's just in the human food area. The largest extrusion installations tend to be in the animal feed areas. Things like dry and semi-moist pet foods are extruded. Also, some of the canned pet foods have extruded pieces in them. And also aquafeeds are extruded. So we've got a very wide range of products that come through this process. So let's think briefly about where we've come from. And we can probably trace the the origin of extrusion to someone who was actually concerned with beer. In 1785, a bloke called Joseph Bramah patented a beer pumping system. And to pump the beer, he needed some pipes to pump it through. And so he specified and patented a new method for extruding tin and lead under pressure to make continuous pipes. So that was, if you like, the first batch type extrusion, hydraulic press. And of course, that process is used for a lot of other materials. By the way, he was quite diverse. He is also credited with inventing the flushing toilet. In terms of application in food, though, first continuous twin screw was for sausages, and Dennis will explain what we mean by single and twin screw extruders as we go along. Also some non-food uses. In the 1900s, used for things like pasta and starting in breakfast cereal. The first extrusion in breakfast cereals were used to extrude dense pellets, which were then put through flaking. And I'll just go through briefly the story of what the Americans sometimes call corn curls or cheese curls. And what happened in this case is that there was a company called the Flake Oil Corporation that was making animal feeds. And to make these feeds, they were putting the feed through a grinder, which was flaking the corn. That grinder periodically required cleaning to make sure it didn't clog. And so the operators at that plant put moistened corn into the grinder to clean it out. And that moist corn heated, but it didn't flake anymore, it puffed. So by complete accident, they'd invented the world's first corn snack extruder. Now, one of their employees was obviously fairly entrepreneurial. He saw those come out, took some home, seasoned them, and turned them into an edible snack, which he called corn curls. And that led to a patent. And it refers to a device which is self-heated by friction between the particles of the material and the surfaces to progressively build up pressure. And that's a key to what's happening in an engineering sense inside the extrusion system. And again, Dennis will talk more about that soon. That firm eventually changed its name to Adams Corporation, which has been associated with producing snack food extruders for many decades. There are other versions of the story. Another one was a firm in Louisiana who made a product called Chiwis, which they claimed to be the first. They got taken over by a company called Frito, which changed the name of the product to Cheetos. So that's still on the market now. And of course, later on, Frito joined with Lay's, so we have one of the largest multinationals in the food industry worldwide of Frito-Lay in this snack food area. Just to keep on going from that time, single screw oil presses. An oil press is essentially an extruder, but with holes in the barrel for the oil to come through. Also using extruders for animal feeds in the mid-1900s. As last century progressed, more use of extrusion in breakfast cereals, in what we refer to as ready-to-eat breakfast cereals, and textured vegetable proteins. It was the 1970s when there was a significant change in the actual design of the machines. Up until that stage, the extruders tend to be, the screws were machined out of one solid piece of metal. In the 1970s, they started to produce what are called second generation extruders, which had segmented screws and barrels so that they could be reconfigured in different ways. Twin screw extruders started to get more use in the food industry in that time as well. And 1990s, some more equipment development. And it's around that time that there was some work undertaken at universities to look at how to optimize screw geometry. Extruders didn't look a whole lot different, but a greater improved performance and throughput during that time. And through to the present, when there are, for example, conical twin screw extruders that are used. There's been developments in wear-resistant components because extruders do wear out. So there's been a continual development of the technology over the last couple of centuries. Dennis will come back soon to a bit more of the specifics about the actual equipment. But before we go there, I wanted to talk a bit more about, if you like, the chemistry of what's going on inside the extruder. Because, of course, if a company is using this technology, they're doing it for a purpose. It's about making products and making products that meet the expectations of the market. To do that, we've got to feed the extruder with the right ingredients and also the right quality of ingredients. So I want to talk a little bit about what is happening to those ingredients through the extrusion process. And we can think of the basic ingredients that go into an extrusion system as having four major functional ingredients. That is, that have a function in the extrusion operation. A lot of our extruded products are starch-based. Some have significant amounts of protein or are protein-based. Often fat is in the system, and fat can be quite negative, as you'll see as we go along to the extrusion process, but it has a significant effect, often on the negative side. And we shouldn't forget that moisture is also a key component of what we put into the extruder. As well as those four major functional ingredients, there's some other minor ones. Minor in terms of quantity, percentage, but can have significant functional effects. Things like salt and acid and sugar and rising agents and flavours. And there's also, when we put in a raw material, they're not pure starch or pure protein, they're a whole mix, and they include some other non-functional materials, cellulose, some fibre that has little or no functional effect in producing the product, but they're there and they're virtually fillers in the material. With the limited time today, I want to discuss what happens to those first two key ingredients as they go through the extruder, the starches and the proteins. And then I'll finish off my section with just some simple examples of some different type of extrusion processes and the products that are therefore produced. So starch. Being from an engineering perspective, you may or may not have had much to do with what starch actually is. It is the primary form of carbohydrate in most extruded products. So it's an important part of our mix. Starch is fairly indigestible when it's raw. That's why we cook our wheat, make bread. It's not only making it easier to eat, it's making it more digestible. So therefore, the cooking effect during extrusion is essential. Most of the starch we use in extrusion tends to come from cereal grains, but there are other sources, things like tuber starches, like potato, tapioca, those sorts of materials. And starches are present in the material, in the raw state, as granules. And those pictures at the bottom of the screen show some pictures of starch granules from different sources. And the starch granules vary in size and shape depending on where they come from. So visually, under a microscope, we can see differences in starch. So not all starches are the same. And different types of starches behave differently. So tuber starches tend to gelatinize very easily. I'll explain what that means in a minute. Grain starches tend to require higher temperatures to cook them. So there's differences. This is a micrograph of starch granules in a potato cell. So they're there as physical balls. And in this one, this is actually pasta. And you can see the balls, large and small ones, a mix of some potato starch. Sorry, this isn't pasta. I was thinking of a different photo. But this is a mix with potato and maize. So we've got large potato starch granules, smaller maize starch granules, and the protein component, the soy, is not granular in this case. Now, starches come in two types of molecular configurations: amylose and amylopectin. And most native starches consist of between 15 and 30% amylose, and the remainder of the starch is amylopectin. There are some variations to that, as there always is in the natural world. Both of these starch molecules are made up of what we refer to as glucose units. So in the diagram there, each of those little components is a glucose unit. The amylose tends to be a linear chain of those glucose units, but a long linear chain, often curved into a helical shape. They can be between 250 and 2,000 of those glucose units. Molecular weights in the tens to hundreds of thousands. So in molecular terms, they're very big molecules. The amylopectin can get much, much bigger. It's a branch structure. So it's not just a single chain, but it's a branch structure and can grow to molecular weights in the tens of millions. So these starch molecules are very big. And to understand what's happening to them when we cook them, I want you to do a bit of a thought experiment. Use your imagination for a few minutes. So forget starch for now. And I want you to imagine that you've got a large container, a drum, filled with water. And suspended in the water, you've got some balls. Let's think of them as a large drum, and you've got some tennis ball size in there. And you're going to put a stick in there and mix it around. How easy will it be to mix? And basically, it's going to be relatively easy. Lots of free space A lot of water, not many balls in there. But those balls have a special property that allows them to absorb hot water and to swell. So as the mix heats, the balls get bigger. And let's imagine they come to the size of, well, you'll call them footballs. Over here, we call them soccer balls. That is, the free space inside the drum is reduced because the balls are now a whole lot bigger. So will it be easier or harder to agitate? And of course, less free space. It's going to be a lot harder. But those balls keep wanting to absorb water, and till they get so big, they weaken and explode and collapse. So will it now be easier or harder to mix? Be easier again, because now we've got that free space back. And so if you drew a graph of ease of agitation versus time as you go through that process, initially it would be very easy to mix. Then over time it becomes progressively more difficult until it reaches some maximum, and then it gets progressively easier again when those balls collapse. Now, of course, that's a picture of what happens when we cook starch by what we call gelatinization. So here's a more scientific view of starch gelatinization. You start off with those raw starch granules, the balls, and they've got a mix of this amylose and this amylopectin in there. If you cook starch in lots of excess water, then those granules start to absorb that water. The molecular structure of the starch gets looser, disrupts the helices of the amylose, the granules swell, and the amylose actually starts to diffuse out of the granule. Therefore, the granules collapse again. They've mostly got amylopectin. So now, when we gelatinize starch, we've got these collapsed granules of amylose, of amylopectin, surrounded by the amylose, which forms a gel, therefore gelatinization. That is, we go from raw starch granules, which are separate entities, to a more homogeneous gelatinized mass. And that's what we're doing when we make a gravy or a custard on the stove. We're gelatinizing the starch. Now, of course, those changes in ease of agitation, or let's call it viscosity, can be measured. And I've got this in here just again to reinforce the fact that different starches are very different. These are amylograph traces, and you'll see that different starches, most of them all at just 6% concentration, so 94% water. Remember, for gelatinization to occur, we need lots and lots of water. And different starches give us different peaks, and it takes a different amount of time for those peaks to develop. Notice the highest one there, the potato, it's actually only half the concentration of the others, but has the highest peak of all. So if we start to swap different types of starches in our mixes, we can expect that it's going to behave differently because starches are all different. So that's one thing we like to stress when we're looking at this technology. It's not just a simple matter of putting the right amount of starch and protein and a few other things into the extruder. It's got to be the right type of starch. And as you'll see soon, also the right quality of ingredients. However, having said all that, I'm now going to tell you that true gelatinization doesn't happen during extrusion. Now, this is an area where we come to a disagreement with a lot of the textbooks and papers that are around that talk about gelatinization during extrusion. A part of that is because many people say that as soon as the starch cooks and loses its structure, it gelatinizes. But true gelatinization requires it to go through that swelling reaction. In extrusion, that can't happen. And there's a couple of reasons for that. Firstly, I stressed earlier that you need lots and lots of water. You need more than about 60% water to get gelatinization, true gelatinization to happen. In most extrusion processes, we've got less than 35% water. More commonly 25, even 17, 18% moisture content of the product in the barrel. There's not enough water present for the starches to truly gelatinize. The other thing is that swelling gelatinization process takes time. If you're cooking a gravy on the stove, it's taking 5 or 10 minutes or more. In extrusion, we've typically got residence time inside the extruder barrel of about 20 to 30 seconds. That is, there's not time for it to go through that process. The key point of difference, and again, Dennis will explain more about what we mean by this, is shear. As the product goes through this screw inside a barrel, the material is subject to shear. And that shear actually physically breaks down the granules. They don't swell and then collapse as gelatinization. They tend to be mechanically broken. And in fact, even the molecules can be broken. And there's a picture here of starch degradation or starch cooking pathways. That is, if we have a high moisture cooking process, it can go through swelling and pasting as a gelatinization process. However, if we go at low moisture content, but instead use shear, we mechanically break down the granules. We melt it rather than paste it, and we talk in extrusion of there being a melt in the barrel. So we're essentially melting the mix, and we produce a cooked material. Or we get some mixture of those two. So there's an infinite number of different pathways that the starch can go through. And we can understand this in mechanical type terms. This diagram seems to say they all reach the same point. That part isn't true. That mix is not all the same. If you do a molecular weight profile measurement on the products of a starch cooked by those different pathways, you'll find that the molecular weight distribution is different. And that's because some of the molecules actually get broken down into shorter chains. And we'll come back to that briefly in a minute. This is some data that Dennis measured, which just looks at the gel versus melt fraction. Notice that at less than 60%, you get less and less gel, more melt. So what does the starch actually do in terms of the extruded products? Firstly, it's largely the starch which determines how the product will expand as it comes through the extruder die. And that's affected not only by the starch and type, but by the amylose amylopectin ratio. Because what happens as the product comes through the extruder is that it comes from a high pressure, very high temperature inside the barrel, comes out to atmospheric pressure. Because it's high temperature, some of the water in it will almost instantaneously boil into steam, and you get a puffing effect. Then that will tend to collapse back and then set at some final. And that's all about, controlled a lot by the starch, the amount and type of starch that's present. But it's not even that simple or complicated. Different starches behave in different ways internally. So you get different bubble size formed, therefore different textures being formed within the product, depending on the ingredient being used. So corn and rice both puff well from an extruder, but if you just puff corn, you tend to get large bubbles, a coarse texture. Rice, much finer texture. So if you happen to take the trouble to look next time you're eating some Cheezels or Cheetos or one of those products, the ingredients list, most commonly there's a mix of corn and rice, and each manufacturer chooses a mix that will give them the textural characteristics that they are looking for the market that they're supplying. Starch has some other functions though. In some extruded products, the starch is important for binding. So if, for example, you are making a pellet to feed the fish and you want to fire it through a cannon into a fish pond, it's got to have it's got to be strong. And starch can be an important part of the strength of the pellet. And there's also what we refer to as, we use words like mouthfeel in a snack. If you think about what you're looking for when you're eating something like a Cheeto, you put it in your mouth and it almost immediately breaks down, almost melts in your mouth and releases all that delicious fatty flavour that they've coated the snack with. That happens because of an effect through extrusion we refer to as dextrinization. Remember I said that the extrusion process, the shear, also breaks down the starch molecules into shorter chains. That is, the long chains of glucose units get broken into shorter chains of glucose units. And what's a short chain of glucose units called? A sugar. Or in between sugars and starches, that's what we call dextrins. The shorter the chain is, the more soluble the material is. That is, by causing dextrinization in a snack product, we're actually breaking the starch down so that it does break down more quickly in our mouth to release the flavours. However, if you're making breakfast cereal, that's a problem, because the breakfast cereal industry has a term they refer to as the bowl life of the cereal. And the bowl life is basically how long it stays crunchy in the milk, in the bowl, once you put the milk on it. And the more you have dextrinized the starches, the quicker it will get soggy in the bowl. That is, the effect of dextrinization is good for one extruded product, for expanded snacks, but it's bad for another expanded product, that is, ready-to-eat breakfast cereals. So this process needs to be changed according to the requirements of the product. But we've got limited time. Let me just talk a little bit about what happens to proteins as well. Some similarities. Some proteins are globular in nature, some are fibrous. The plant proteins tend to be more globular. And again, if we add moisture and heat, those granules, those globular proteins will hydrate, and under the action of heat and shear in the extruder, you start to unfold the complex tangle of the protein molecules. And then, if you give it the right conditions, you will break down the granule and release that protein, unfold the protein. And if you've got the conditions right, you can then encourage all those protein molecules to line up in one direction and to cross-link, and that's how we form a texturized piece. So when we talk of texturized vegetable protein or meat analogues, what we're doing is unfolding the proteins and encouraging them then to link up together to produce a fibrous meat-like texture. And we can do that using the right conditions in the extruder and in the die as it comes through. And this one is the picture of a pasta. A pasta, we don't want to cook the starch. The starch granules are still intact. They get cooked in the water and they're glued together by fibrils of protein, commonly gluten. But protein will only work effectively if it's of the right quality. If the protein has been previously cooked, it can't form that texture. It can't go through those range of reactions. And I'll skip over this a bit, but we can measure the quality of proteins by things like protein dispersibility index, or NSI, nitrogen solubility index. They're both essentially measures of how soluble the protein is. Uncooked protein is highly soluble. Cooked protein becomes insoluble. Think of it like, think of egg white. If you take egg white uncooked, you can easily mix it with water or milk. If you cook the egg and then try and mix it with water, it's not going to dissolve. So the solubility is a measure of whether the proteins have been previously cooked or damaged. And this is a photo of a pet food coming through an extruder die. And you can see here it's coming through a die, it's puffing out, and then it's collapsing back. This photo hasn't got the cutter knife running. If that was rotating, it would be cutting off pellets of dog food. And that's typical in a pet food extrusion process, because the protein that's used is commonly cheap meat meal, and meat meal has been rendered at a high temperature, so it's already cooked and it's not functional. However, if we swap out that meat meal and put in a highly functional, high protein dispersibility index vegetable protein and use exactly the same process through the extrusion, this is what comes through. The quality of the protein completely changes. So this was the same protein level, all the other ingredients the same, except that the protein part was of different quality, and it completely changes the way the process behaves. So we won't go into further detail here, but just to say that all these ingredients have a function in the extrusion operation. Understanding how they work within the process is important to making sure we can get the process running consistently. And just to finish off my section, I want to just give some very brief examples of these different processes. So at one end of the scale, if we apply low shear, low mechanical energy, which in extrusion is often referred to as SME, specific mechanical energy, if we use a screw configuration and conditions to keep the shear low, use a high moisture content and keep the temperature low, we avoid damaging the starches because we don't want to cook the starches in pasta in the extruder. We want to cook them later in the water. We don't get much expansion because the temperature is low, so we make a very dense product. And we end up with a pasta. If we use a process with the extruder configured to give us a bit more mechanical energy, and that energy goes into temperature, so we develop higher temperature at medium moisture contents inside the barrel. We develop higher pressure to force that material through the die. Then we'll get some expansion. We'll get a well-cooked product so that it's well digestible, and we make things like pet food through that sort of process. On the other hand, if we go to a much even lower moisture content in the barrel, apply very high mechanical energy, develop very high temperature and generate high pressure, then we can get a lot of expansion. We get a very low density puffed product like an expanded breakfast cereal or snack. And there's one other special one, different process I want to mention. And this one is very topical at the moment because there's a lot of interest in alternatives to meat. This extrusion process is fundamentally different to most other extrusion processes in that it is operating at high moisture, generally well in excess of 50% moisture content in the barrel. We refer to it as high moisture extrusion cooking. We're also using very high protein content and highly functional proteins. And because we've got high moisture in the barrel, as we get the temperature up inside the extruder, we can get high moisture cooking reactions to occur. We need to develop very high temperatures to cook the protein, unravel those protein molecules, but we don't want to destroy them, not too much mechanical energy, because we want to then line up those proteins and produce a fibrous type of structure. And we do that in the die, not in a small hole, but in a long, cool die. And in this case, as the melt passes through the die, it solidifies. The velocity profiles that are developed encourage those protein strands to line up and allow the cross-linking to occur between those fibres, and we get the meat-like texture. Now, in this case, this product is made at high moisture, and therefore it's also got potential to spoil, essentially like a meat. So therefore it needs to be preserved by some other method. But this is the sort of process that's used for making some of our meat alternatives. And by changing the conditions, we can change from, say, a pork-like texture to a chicken-type texture. So I'll stop talking at that point. I really just wanted to give an overview of this extrusion process and the types of products that we can produce through that process. And I'll pass over to Dennis to talk a bit more about the equipment and, if you like, some of the more engineering aspects. But I hope you've also, and one of the things that took me a bit by surprise when I started to work in this area, even things like the way we cook starches can be thought of in mechanical type terms. So I'll pass over to Dennis, if you're ready.
I'm ready. Well, thank you, Gordon. And for those of you who do have any questions, there'll be an opportunity at the end for you to ask whatever questions may be on your minds. Okay. Put this one up on, and hopefully you can all see that at this point in time. So what I'd like to do is take the next step in terms of our understanding of this technology by starting to get into some of the nitty-gritty as to how the extruders actually function rather than just their applications. As Gordon's already touched on, the technology can be used for manufacturing a broad range of products. You know, I've personally, in my working career, been involved in using extruders to make everything from boiled lollies to explosives and a whole manner of things in between, both food, non-food, feed, all kinds of functional ingredients as well. So it's a very flexible and quite cost-effective technology. The extrusion cooker is simply a continuous reactor within which the process designer has provided the prerequisites to control the numerous reactions that are taking place. And Gordon's already walked you through some of these so-called cooking reactions that are highly dependent on the formulation ingredients, and more specifically on the components of those ingredients, and also their quality. And this has a direct influence on the finished product attributes in terms of flavor, color, shapes, textures, etc. The cooking time is very, very short, typically less than a minute within the extruder barrel itself. There also are aspects of extrusion such as the preconditioner that Gordon touched on that can extend the cooking time and allows us some flexibility in terms of the detail of the energy flows that the product sees, thereby changing the product characteristics as well. So via the provision of a selected screw profile, which incorporates a broad range of different types of elements that we'll come to see in a moment, and with varying clearances within the gaps, and by utilising both motor power and barrel heating, and if we have a preconditioner, also some convection energy as well, we could influence those cooking reactions that Gordon talked about. So the numerous engineering aspects of the process, like heat transfer, mass transfer, momentum transfer, residence time and residence time distribution, have a strong impact on the food or feed properties, both in terms of their appearance, but also in terms of their functionality within the consumer, because the digestibility of the feed itself is not only a function of the ingredients that we put into a product, but also it's all related to how we cook those raw materials. Simplest way of describing the basic working principle of an extruder is to say that they rely upon the action of friction within the system. And coming to grips with that is quite simple, because if you simply take your hands and rub them together, your hands get warm. And that's you generating frictional heat between the two surfaces, namely your hand. And the greater the friction, which we can achieve by either pressing our hands together more aggressively or rubbing them more aggressively, directly influences the amount of heat or friction generated by what we refer to as viscous dissipation. And the same is true in the extruder, where the two surfaces of relevance are the rotating screw and the barrel wall. And it's the interaction of the formulation ingredients in this shearing zone that leads to the viscous dissipation that generates the frictional heat and temperature that leads to the cooking processes that we're after in the first place. So a typical direct expanded product, as Gordon explained, so your typical snack food or pet food or those sorts of products, occurs via what we call direct expansion process. And we can see a direct expansion extrusion occurring here. We can see a corn formulation being directly extruded out of the die. And we can see, not too well because of the steam, and it's the generation of this steam that leads to the boiling of the product and the formation of the internal structure of the product, the open cellular form that you'd be used to. And we attribute with textural attributes of the product, so how crunchy they are, etc. In some applications, these internal bubbles are not so much there as a means of developing texture, but rather it's where a significant part of the formulation is subsequently added. So in an aqua feed, the porosity of the product is very important, because there has to be sufficient volume within the finished pellet to incorporate all of the oil that's required to meet the formulation requirements to feed the animal. And so the understanding this boiling process is very, very important. Now, as you've seen from that brief video, the process is quite dynamic. And not only does the product expand out of the die quite aggressively initially, but there are also other forces at play, namely elasticity, that results in the collapse of the product as well. And finally, there's significant heat transfer occurring, because the product that before it leaves the die, as it's flowing through there, is typically significantly above 100 degrees, which is the boiling point of water at atmospheric pressure. So the water that's in the product, once it leaves the die, is instantly, or almost instantly, transformed into steam, leading to this boiling and the bubble formation. But as the steam is released from the product begins to cool quite rapidly. And coincidentally or not, it turns out that at the equilibrium temperature of the product as it leaves the die, which is typically in the range of about 90 to 95 degrees, this is the freezing point or glass transition point of proteins and of most proteins and starches. And so as a result, the product becomes more rigid and robust. And so the product starts to collapse as it's cooling. And eventually the cooling process stops and the shrinkage stops as well once the product reaches this equilibrium temperature, and thereby defines the final product dimensions. Now, extruders come in many different forms, as we'll see shortly, but they can basically be categorized most simply as either being single screw or twin screw. It's sometimes advantageous to use a multi-stage process. So rather than just a single extruder, we can often couple two or more extruders together to achieve an objective. It's also possible to carry out these sorts of more complex processes on one screw to do the whole job. But this, by having multiple extruders in the process, this allows optimization of the individual steps within the overall cooking process. And so, although more capital intensive, it does allow better process control. When we talk about twin screw extruders, they come in four major types, and these are the co-rotating or counter-rotating extruders. And then they can either be intermeshed or non-intermeshed, hence the four variants. The typical extruder used for cooking applications is the co-rotating intermeshed twin screw, as we can see in this brief video. We can see the two screws are tightly intertwined, and also the screws are rotating in the same direction. And we can also see a couple of different machine elements on this particular design as well. Oops, my apologies. Okay. Now, Gordon touched on earlier about many extruders being modular in their design. And so just like a box of Lego or a Meccano set or whatever you grew up playing with, you can arrange all of the components in different orders and get a different result. And this is essentially what we do when designing extrusion processes. We've got all these functional components, and by changing the order that we place them within the given extruder barrel, by rearranging the elements on the shaft, or by changing barrel configurations or temperatures and so forth, we're able to influence the processes and the fluid dynamics that are occurring within the barrel itself, thereby ultimately changing the product. There are a number of aspects of the screw geometry that we need to come to grips with. And first and foremost is the diameter. So usually if I refer to diameter of an extruder, I'll be referring to the screw outer diameter. So it's just the tip to tip distance. The barrel diameter is always somewhat larger than that, thereby generating what's referred to as a flight clearance or gap. Now, this is the most important part of the extruder because this is where the shear is going to be generated. The frictional heat is generated within the confines of this narrow gap between the barrel wall and the high-speed rotating screw. The duration of that shear is directly influenced by both the thickness of the flight land of the screw and also the number of screw elements or flights within a given length of the screw. So the more intense cooking processes are achieved by multiple flight screws, and also there are further optimizations that we can talk about shortly. And all of this geometry also relates to twin screws, by the way. The channel depth and the pitch or channel width of the screw, these are the primary criteria that determine the volumetric throughput capacity of the machine, because basically the volume within the flight of the screw multiplied by the RPM is the theoretical conveying volume of the auger or screw. And this is an important feature of the design of the machine. And so as we manipulate the geometry, the detail of the geometry through the length of the machine by using different elements, we're changing the volumetric flow rates in different parts of the machines to influence the process. And so if we think about the unit operations that we desire to be occurring within typical extrusion process in order to transform our recipe into the melt that Gordon talked about earlier, requires some, if not all, of these processes to occur. Now, depending on the specific application and the configuration of the machine, some of these unit operations will be more important than others. But basically, we're expecting the extruder to act as a mixer to compress and degas the material. The extruder is expected to provide the kneading and shearing that creates the viscous dissipation, that generates the heat, that creates the cooking, that forms the melt. The melt then has to be pumped through the die. And also we have the ability to heat and cool the barrel walls of the extruder and sometimes the screws as well. We can do steam injection or removal from in situ during processing. We're also able to provide multiple injections and multiple material feeds along the screw length if the extruder is suitably configured. Now, there are multiple different types of extruder screws, and we can see that this compression duty can be achieved in a number of different ways. So we can either change the shaft diameter or the barrel diameter or the screw pitch length as a means of changing the compression ratio within the screw. And this directly influences the way the materials are degassed and the way the product is cooked as well. We can also influence the process through the design of the barrel wall, especially in single screws. In twin screws extruders, they're typically always smooth. Smooth walls are also available in single screws, but they are more commonly have rifling that can either be longitudinal or in the spiral pattern within the barrel itself. The die geometries also can be manipulated and changed depending on the style of product that we want to make, whether we want to die face cut, whether we actually want to make a shape at all. And so by changing the geometry of the die, we can change the detail of the product as well. And if we consider the optimal behavioral design of an extruder, the basic components that should be present in an extrusion system would include a feed section, and the design of the feed section should be such that it allows for the raw materials to be fed directly into the extruder along with any added liquids and simply conveyed away from the infeed zone so that the next quantity of material can be fed in next. It also needs to have sufficient volume within the screw to also allow the discharge of gas from the solids that are being compressed in the next section of the machine. Because as materials are fed forward within the screw, the particles are compacted together so that they are forced to interact with each other so that there's not only shear at the barrel wall due to the action of the screw, but the body mass of the movement of the materials within the screw leads to interparticle interactions, and these particle interactions generate shear within the body of the product itself at the particle level. And to maximize or encourage these interactions and to optimize those, we have to bring those particles into closer proximity. And we do that by this compression zone. And so by balancing the rate of compression, we can influence the interaction of the particles and therefore the way they're cooking, plus the friction that's occurring at the barrel wall is going to accelerate that process. And by balancing all of those, we define the transformation or cooking of the material into the melt that we're after. That melt is then pumped through the die via what's referred to as the metering section at hopefully a controlled flow rate that allows the preparation of the final product dimensions and shape and expansion characteristics and so forth. So in a simple animation of what goes on in an extruder looks a little bit like this. And you can see the solids being fed into the screw. You can see that the screw is not completely filled, so there is sufficient void in the screw to allow the degassing of the raw material as it travels through the progressively compressing zone of the screw. This starts to generate frictional heat and melting of the materials, and the formulation is being transformed into the melt, and that melt is then able to flow or be pushed through the die assembly to become the product that we were after. And this is what's occurring when the system is operating in a steady state. In the case of the twin screw, as I mentioned earlier, there are 4 different types, and here they are. So we have the intermeshing type of screws in the upper part of the schematic, and they're either co-rotating or counter-rotating, and the non-intermeshed screws in the lower part of the schematic. Now, the typical cooking extruder is the co-rotating and intermeshed screw. Each of the other types of extruder also do have applications, not typically for food applications, but they have other operating characteristics that make them more useful for other forms of processing. We talked earlier about the perceived simple flow dynamic that occurs in the single screw. We saw an animation there that suggests that the material simply spirals its way down through the channel of the screw as it's moving from infeed towards the die. In reality, the flow dynamic is more complex than that. And if it was true that it did simply spiral along in the screw in simple flow, then that would not be possible in the case of the twin screw, especially not the intermeshed twin screws, because as the product would spiral with the first screw, it would subsequently encounter the flights of the second screw in the machine. And in reality, it couldn't get through. So the spiral can't be completed. The only way the product can continue to flow is by moving from one screw to the other and then continue the rotation in the second screw, and then it encounters the first screw again, so it has to swap from the second screw back to the first. And so material is continuously moving position from one screw to the other and rotating and being sheared, and the shear within the material itself. So the flow dynamics are quite complex. And the behavior of a twin screw, again, is shown in this simple animation. It looks a little, oops, back, my apologies. It looks a little bit like this. And so we can see the material dropping into the closer screw and then reappearing in the backside of the second screw, and then is transferring from the second screw back to the first to continue its revolution on through the machine. And this movement of material from screw to screw means that the flow dynamics within the twin screw are even more complex than those in the single screw, but they are certainly different. And this explains some of the differences between products that are processed on twin screws versus single screws, and the differences in their final product characteristics. The rheology, or viscous and elastic properties of the raw materials that we encounter in the extrusion process are very, very important in defining the final product characteristics. These rheological properties have a direct influence on bubble growth rates, and this determines the cellular internal structure of the product. It has a direct influence on the overall degree of expansion, and also on the degree of curvature of the finished product itself. The rheology of the extrusion melt also has a direct influence on the process design, because it directly influences the die pressure drop. It has an influence on the screw flow dynamics that we now have seen are quite complex. And finally, also the screw energy consumption, or the power per kilo, or the SME that Gordon touched on earlier, which is a coarse measure of the degree of cook of the product, are all influenced by this rheology. So just a quick review of rheology and what it's all about. So if we think of a fluid as consisting rather than as a continuum, but imagine that fluid exists like a deck of cards. And if we were to apply a force to the uppermost card in that deck, then we would expect that card to move at a particular velocity, and that velocity would be dependent on the magnitude of the force that we apply, but it also would be directly influenced by the resistance to flow between one card and the next. So if we apply force to the card, the top card tries to move, but in so doing, it will drag the second card and subsequently the third and fourth and so forth. And so all the cards are seen to move at a particular velocity profile, which is dependent on the internal fluid friction. And this is what we observe as viscosity. Gordon talked about in the example of the hypothetical example of cooking, where the shear or the force was being applied by the broom handle, and the force or the effort required to move that broom handle changed with time as the tennis balls absorbed water and swelled and cooked. So this is evidence of a changing viscous property in the cooked material as the cooking process occurs. And this is what's occurring within the extruder as well. So the fluid rheology is not a constant, it's a changing parameter along the length of the machine as the material changes from a free-flowing powder to a compacted powder and finally to a melt. The rheological properties are continuously changing. Hence, the fluid dynamics that we touched on earlier are also changing as influenced by this rheology. Now, when engineers see forces and areas, this defines as stress. When there's velocity profiles involved, then this defines as shear rate. And in the extrusion system, there's not only the flight gap shear rate that we've touched on a number of times, where the frictional heating is occurring between the high-speed rotating screw and the barrel wall, but there is shear throughout the channel as well, depending on the radial position. And the minimum shear in the extruder is at the base of the screw channel. So as the screws become more shallow, they become more aggressive or higher shear. If the screws are very deep channeled, they are a lower shear mixing or extrusion process. There's also a shear rate associated with the melt flow through the die itself, because as material flows through the die, which can be considered, and a die can be considered as a short, often complex pipe. And like all pipe flow, material tends to flow faster in the middle and slowest at the edges. Therefore, we have a velocity profile or a shear. And so this shearing action occurs within the die as well, predominantly at the outer edges of the die, and results in the skin formation. So if you, next time you eat an extruded product, take the time to look at the individual product itself, and you'll find the surface characteristics of the product are different to those of the core of the product itself. And this is because the core product has seen all of the channel shear rate and the flight gap shear rate, but only the surface has seen the die shear rate. The core of the product did not. And it makes a significant difference to the visual and functional properties of the material itself. Now, there are a myriad of different types of fluids out there, ranging in complexity from simple Newtonian fluids like water and oil through to highly complex fluids with all sorts of weird and wonderful properties. Most of the materials that we process in the extruder are non-Newtonian, and so they show shear dependent viscosity and also temperature dependency and moisture content dependency and temperature dependency. And the detail of that rheology is directly influenced by the formulation, ingredients that we use to define the product, and also on the quality aspects of those ingredients, as outlined by Gordon earlier, in terms of the measurement criteria, such as the protein dispersibility index and so forth. These directly influence the rheological properties as well. And Gordon walked you through this sort of stuff earlier on, so I won't harp on it too much. I touched on the fact that I keep talking about rheology, and it's not just viscosity. So rheology also has an elastic component. And when you take an elastic material and apply a stress to that material by stretching it, shearing it, or squeezing it, then elastic materials will respond once they're allowed to, and to those stresses. And an example of this in a particular extruded product, you'll note these. Note the safety sandals that everybody's wearing. This test was carried out by Gordon and I in Thailand. And what we have here is a high protein material, high PDI protein material. So it has a lot of functionality and hence a lot of memory. And the fluid, even after having flowed through a long cooling die, still has a memory and remembers that for the last 30 seconds or more, it's been going round and round inside a screw. So the fluid is said to have a memory. Now, within the extrusion process itself, there are a number of flow dynamics, and there isn't sufficient time to go through them all today. Suffice to say that this whole extrusion process is basically can be readily understood if we can understand and take the time to understand what we refer to as the 4 golden rules. And this is the first one that describes the volumetric flow components within the extrusion system. And basically, we put raw materials into the extruder at a particular mass flow rate, and dependent on the bulk density of those solids that we put into this extruder, that will define the volumetric flow rate into the screw. As a result of the cooking process, then that material is then also transformed into a fluid, both by compression and melting and all mixing and all the other activities that are occurring inside the screw. And usually the density of the material will increase at least twofold. And as a result, the volume flow coming out of the extruder die before the expansion process commences is approximately half that of the volume that comes in. And also, there's a significant loss of gas from the system. And so the output volume from the extruder, which is the same mass flow, but now we're dealing with a much more dense fluid rather than a free-flowing powder. As a result, the volume flow out of the extruder is significantly less, and therefore there has to be a balance of these volumes. And there's also a reverse flow component, which we've not really mentioned too much yet, but there is a leakage flow between the flight gaps, which is where the cooking process actually occurs. And there's a pressure profile driven flow within the screw channels, which we refer to as the pressure flow. And it's the balance of those three, the forward conveying of the action of the screw, the reverse flow components because of the resistance to flow of the die, that results in the internal flow components that lead to the cooking of the product. Once that melt is formed and the formulation's been transformed into the fluid, it is pumped through the extruder die. And these fluids are very viscous. Now, in terms of order of magnitude, a typical extrusion melt will have a viscosity of somewhere between 50,000 to 200,000 centipoise, or 200,000 times thicker than water. So very viscous fluid. And most of these fluids are being forced to flow through very small dies or orifices. And as a result, the operating pressures required within the extruder are very high. It's not uncommon to see an extruder operating at 30, 40, 50 atmospheres of pressure, are not uncommon. And this reflects both the high volume flow through complex small geometry, but also the very high viscosity of the materials being dealt with. And those flow dynamics that we touched on earlier are significantly different between a single and a twin. And so even if we have the same processing, theoretically, same processing history, the actual finished product characteristics are different on a single versus a twin. So in simple terms, another simple analogy that you can use to understand an extrusion system is that every screw element within the extruded geometry acts like a pump with slip. And so an extruder is simply a multi-stage pump with slip. The magnitude of that slip depends on the local viscosity, the local pressure, and the local geometry. So by us changing the screw geometry, we change the balance between forward and reverse flow components to influence the transformation of the product or the cooking process itself. And so the extruder will backfill or utilize as many stages of the screw elements that is needed to deliver the required volumetric throughput against the current operating pressure. And this ends up controlling the field length of the machine that defines the average residence time within the extrusion cooker. And then it's the residence time distribution, which we can influence by the specific screw geometry, that influences the final cooking characteristics of the material. Now, for most extrusion processes, the average residence time is quite short and usually less than 1 minute. So this cooking process of starches and proteins that Gordon described earlier normally takes a significant amount of time. And so the extruder, however, does it in less than a minute typically. So clearly the processes and the chemistry and physics involved are different. And this is why we like to stress that extrusion is all about cooking, but it is not gelatinization, nor is it denaturation. It's something else. And so to reinforce that, I'll present a couple of simple examples of various extruded and non-extruded products to show the differences. And the first one is something as simple as pasta. So if you want to eat the best pasta, the way to do that is to buy a decent durum semolina flour, mix it with water by hand. And as a result, the mixing process is very slow, the outputs are small, and the key important thing to do is to not allow the mass to get above your hand temperature. This is why Nonna makes the best pasta. And on the other hand, if we then go to a sheeting roll as a means of forming a pasta dough, then the process by multiple passes in a sheeting roll is much faster, but the mechanical work input resulting from the sheeting rolls leads to some temperature development, some damage to the starches and the proteins, and an elevation in temperature which starts to cause some of the starch granules to begin to rupture and release the starches. So we start to do damage to the starch. And so rather than pasta, which is meant to be a protein glue with starch granules embedded within it, it now starts to be a mixed system. If we then accelerate the process even faster and we put the same flour or water mixture into an extruder, we can generate much greater volume of pasta, and we can make pasta in many multitude of other shapes instead of just sheets. And the net result is much more interesting products, but a degradation of the product quality, however. And this is evidence here. So we have an independent trained test panel. They got to taste product produced via these three different processes, and the differences in the cooking processes are reflected in the product quality in terms of the way they cook. So the cook times are very different, the texture of the products, the stickiness, and the overall product quality. And you can see that the handmade pasta shows no sign of stickiness, has the best texture by whatever mechanism that was, and the shortest cooking time, and therefore the best rating, versus the extruded pasta has the longest cooking time, the lowest quality texture, does have some stickiness associated with it, and is the least well-liked of all of them. And this is why premium pasta is always handmade. Another example is the manufacture of a cornflake. The traditional process for making cornflakes is to take the corn kernel and to size reduce the corn kernel and basically crack the kernel into 4 components that liberates the germ, which can then be sent off to extract the corn oil from the germ, and thereby generating maize gluten or hominy meal, depending on what industry you're in. That's the byproduct of the corn milling process. The corn grits that are produced can then be put into a traditional corn cooker, and by slowly, over an extended period, typically about 3 hours, at intermediate moisture contents, and essentially at atmospheric pressure, we're able to steam cook the individual corn grits, and eventually we can release those out of the cooker and send those through a flaking mill and each corn grit becomes one corn flake after toasting. On the other hand, we can take those same corn grits and put them through a roller refiner and produce maize flour. Now, the maize flour can be put into an extruder and operated at similar moisture contents, but much higher temperatures. And we're able to produce a cooked corn mass that we can see coming out of the die assembly here. Those ropes of cooked corn are too sticky to be directly cut, and so we're taking them offline, cooling them partially before cutting them, and then those individual pellets can be sent through the flaking mill to form corn flakes. Now, on paper, both of these products are identical, but in reality, the eating quality of an extruded corn flake is always inferior to those of a traditional corn flake. Their bowl life, another term Gordon touched on earlier, how long does it take before the corn flakes go soggy in the bowl instead of being nice and crunchy, is much, much shorter. And this is all evidence of the action of this shearing process. So the extruded corn flake is cooked in under a minute, whereas the traditional corn flake is cooked at lower temperatures with more moisture, a more gentle process over a 3-hour process. And it's done by convection heating rather than mechanical energy. And so this starts to touch on some of the differences. Gordon also spoke about the high moisture extrusion cooking process that's currently attracting a lot of attention. And it's a very good process for either preparing non-meat but meat-like products, very popular for the vegetarians and so forth in the world. This technology is not new. It's been around since the 70s. It's only now found application in the food industry, but it was traditionally used for value adding to low-grade meat and fish byproducts in the pet food industry. And so this technology is being reinvented at the moment for the food industry. So as we touched on earlier, there's a multitude of different types of extruders out there, all kinds of different brands. Everybody's telling you that theirs is the best. Just like with cars, don't believe any of them. We all have our preferences, and it's the same with extruders. Some extruders have particular functional characteristics to make them more attractive for specific applications. But remember, all extruders have to try to do these same unit operations in order to transform our ingredients into the sorts of products that we're after. Now, given all of what I've been saying so far and all of what Gordon's told you as well, you're probably getting a picture that extrusion is relatively complex. And this was a simple model that was prepared by a guy called Bob Miller, who unfortunately just recently passed away. So rest in peace, Bob. And this is his view of what goes on inside an extruder. And without looking at it in too much detail, it's a highly interactive process. Everything you do influences everything else. And this makes understanding extrusion quite challenging. It also makes carrying out experiments to optimize extrusion processes also quite difficult, because under normal experimental procedures, what you like to do is keep everything the same and change one variable. But as you can see in this chart, changing one variable influences 6 others. And so it's a very complex thing. So when it comes to product development, what we have to be very careful about is not only focusing on just trying to make the perfect product. What we should really always be trying to do is studying the interactions of all the variables, and in so doing, defining the design space somewhere within which our optimum product will exist. But it's about understanding all of these variable interactions that defines this design or operating window for the process. And this is critical when we start to look at the scale-up exercise, because the residence time directly influences how the viscous power dissipation directly influences how the product cooks, as we've discussed so far. And so this allows us to make very different looking products, as you can see here, even from the same extruder, even with the same ingredients on the same day, by changing the detail of how we're running the machine. And so a broad range of products can be made. Some of these might be acceptable, some not, some may be preferable than others, but it makes the whole exercise quite challenging, but very interesting. So understanding these interactions between the shear rate that's occurring within the extruder and the residence time, we do this by basically by studying the average total strain of the system. Now, the average total strain is the integral of the local shear rate and the residence time distribution over time. And so this would be wonderful if we just knew where every particle was every moment of the time during the extrusion process, and if we actually knew what the shear rate was wherever that particle went. Life would be easy, but we don't. And so what we actually can do is what we refer to as a weighted average total strain. And this relates the average shear rate with the average residence time, and that defines the weighted average total strain, and that allows us to relate the power involved in the process as well. And as we change these parameters, that will change the product characteristics. And so there's a myriad of ways of studying different defining product characteristics after processing, and we can do all sorts of physical and chemical tests on the materials after cooking to define the quality of the product. And many of these are standard industry tests. So when we're looking to do scale up, we need to grasp all of these concepts and then also understand the very notion of what scale up is. And there's a lot of misconceptions out there. It's not just about making more stuff. It's not just about building bigger equipment. It's about trying to make more of the same product, and understanding that and achieving that true process scale up involves a lot of in-depth understanding of all of the information that we've touched on earlier today. So processes, as they move from conceptualization through to commercialization, we have to prove these products and processes at various scales. And these are a range of different size machines that I've been lucky enough to play with, from as small as 10mm screw diameters up to as large as 380mm diameter screws, and everything else in between. So when intermediate between a laboratory and bench scale and production is the use of pilot plants. And pilot plants should be designed and operate with 5 main goals in mind. That's to demonstrate the process product at small scale, relatively small scale, to allow the collation of all the required engineering data. So this is about defining that operating window that we touched on earlier. It's about understanding all those material process, equipment interactions, and defining them all so that we can replicate those conditions at the larger scale. If we do it right, there's a significant reduction in the project lead time and typically a significant impact in terms of minimizing total project costs. And these are the fundamental reasons why we do scale-up calculations and so forth in any processing application. So when we design experimental trials, we should always focus on getting the process understanding and the understanding of the role and the control of the unit operations involved, because like any engineering process, the processes, although there might be a number of unit operations at play, there will always be key aspects to a process that are really the process determining steps. These can sometimes be mass transfer or heat transfer or shear distribution or whatever it might be for different products. We have to define the required product attributes. So we should spend a significant amount of time understanding things like the product texture, bulk density, digestibility, whatever it is relevant to the particular product we're working on, but understanding and defining it and learning how to measure it correctly so that when we are trying to replicate, we can assure ourselves that we've actually achieved the objective when we finally get there and not just rely on somebody else saying, yeah, I like that, or no, I don't. And which is more often what we get forced to do. It also allows us to get good knowledge and structured knowledge generation to allow easy process transfer and training and business integration. And it also allows us to have more effective troubleshooting and continuous improvement and process optimizations occur. So it's not just about building bigger machines. Most manufacturers do offer their equipment in a range of different sizes, from small laboratory machines through to large production machines. This is standard so that they can offer you equipment to fit the scale of operation that you want to operate your business at. So the primary objective of a scale up or scale down of any extrusion process is to make the same product at a higher or lower production rate. And sometimes it's important to be able to scale down, because if you have a problem in the factory is not probably an expensive place to try and study the problem. Maybe it would be better to study the problem offline in the laboratory and be able to then take the solutions back again. And that requires both process scale up and scale down. So scale up can be defined as defining the geometry and the operating conditions of any given machine or manufacturing sequence that replicate the working conditions of different equipment of the same type, but distinctly different in size for processing the same recipe. So in other words, make more of the same, not just more. So the process methodology should be able to deliver all of the relevant information that we've been discussing so far. It should take into an understanding of all the fluid and heat and mass transfer dynamics occurring in the machine, and should take in the impact of different geometrical parameters and processing variables. Now, to the novice, an extruder is just a screw in the barrels. How hard can it be? But the reality is that every equipment manufacturer makes slightly different geometry machines, and as a result, their fluid dynamics within those machines is different. And as a result, so too are the cooking processes. And so understanding these interactions is also very important. So a brief look at a what I'll call a successful scale-up result is this is a project that I worked on a while ago now, 8 years ago now. But what we did was basically I was approached by a client who asked me to develop a dog chew pet snack for them. And so we sat down and discussed ingredients that might be included in the recipe. We eventually formulated something. We then picked up all the ingredients, flew over to New Zealand because there wasn't an extruder available in the time window that we wanted to run the tests. And so we flew over to New Zealand, got onto a small scale laboratory machine. Now, even though I said we need to get all this really intricate data, the actual physical equipment used to obtain all the important data doesn't always have to look very pretty, and this certainly does not. You can see it's not the cleanest or tidiest of extrusion processes, there's stuff going on everywhere, but by getting all the appropriate measurements from this process that was transforming those ingredients into this product, and we've got a product being extruded here that was shown to be appropriate for the client. They had the right textures, colors, flavors, all that sort of stuff. Dogs were happy, everything was fine. We then came back and the business managers decided, marketing people, everybody else got involved. And so the decision was made to scale up, to implement the project and scale it up. Of course, along the way, marketing got involved. And so you'll note that on the left, we've got a product being produced. This was a 3-pointed star shape. So there's another leg out the back here that you can't see. By the time the project was given approval, marketing had changed the product shape. They also changed a few ingredients just because they can. And as a result, what we then did was go back to Australia, meet the new product spec. And this was a French twin screw sitting in New Zealand. Went back to Australia, I found the second-hand English twin screw extrusion machine. By understanding the flow dynamics and everything else, we were able to get an appropriate screw design for the English machine. And what we can see is now a 10-fold increase in output. So the flow, there's 7 more dies. So you think that was 7 more. But because of the changes in ingredients and so forth, we're actually processing at 10-fold the output of a different shaped product that met the same product criteria. And we can see the process happily extruding. And so this was an example of what I call a successful scale up, in that we produce significantly more of, not quite the same because the specification changed, but it was almost a perfect result. So when we're looking to carry out a process scale up, a thorough understanding must be obtained of those things that change with scale and those things that do not. And for an extrusion process, in order to fully replicate the process, we should try to replicate and maintain all of these criteria at the same time. Now, this list is quite extensive, and typically it's almost impossible to get all of them maintained. Screw geometries change, a whole bunch of things change. So during scale up, there's often some compromises need to be made, but we need to keep all of these things in perspective and understood. And we'll find for any given process that one or more of these are the absolute critical parameters that define your particular product. And that comes through in the experimentation or pilot plant scale behaviors. There are other things that are out of our control, like there's always heat transfer problems when you're scaling up, because the surface area to volume flow, volume ratio changes with the inverse of the diameter. So it's always harder to keep temperatures under control on big machines versus small. And this is a universal problem with scale-up, not just of extruders. So energy flows are very, very critical. It's the energy that results in the transformation of the ingredient into the product. And the energy comes in three basic forms: mechanical, convection or steam injection or removal, and conductive, heating and or cooling as well. And by manipulating the energy flows via the process design, we're able to control the cooking process itself. All of the energy going in has to be conserved. And so by understanding where the energy went, by doing good physical measurements such as temperature, pressure, and so forth, we're able to define what's going on inside the process. And this is our second golden rule. That should be our third golden rule. Sorry, just typo there. That was the previous one, was the second rule. This is the third. So hopefully this has brought things together, and maybe now extrusion's not so much a witchcraft, it's a little bit more of a science, and is certainly understandable to a certain extent. We certainly keeps Gordon and I more than busy most of the time trying to understand lots of things. So I'll throw it open to everybody if there are any questions. I'm more than happy, or will be more than happy to take them. I'm sorry if we haven't quite overrun, but almost.
No, that's not a problem. Yeah, there are a couple of questions. Sandra has a question. Do you want to, unless you can see it, or do you want to see it in the chat?
My question was originally for Gordon, actually. Hello. So he was talking about vegetable protein meat, and I was wondering if he's aware of the quality of any quality control that goes on for the nutrition, the nutritional value of this material.
Yeah. Look, I hate to tell you this, but the nutritional characteristics tend to be fairly well down the scale in a lot of products. Now, there's a couple of things to qualify that. The basic composition of the, protein, fat, moisture, carbohydrates is determined by your input. So they're pretty straightforward and they don't change significantly. The reality is that nutrients like vitamins do not survive a lot of extrusion processes very well. So where the nutrition is critical, like in pet food, there's additional vitamins put in to make up for the amount of destruction. And those will be tested on as part of quality control, but not every day, every batch.
Yeah, I suspected that. Yeah, thank you. Yeah, I work in agri-food. That's why I wanted to ask. Thank you.
Right, okay.
Well, I guess the easy cop-out most of the time is because humans are omnivores, then they go and find some, if the nutrition's not here, we'll go and get it somewhere else. I just eat this because I like it. So there's not much nutrition at all in most of the snack foods we eat. So we eat them all the same.
Yeah.
Okay. I apologise if I got your name wrong, Mr. Brewood. Question. Oh,
you're on mute.
Mute.
Oh, there we go. Yeah. Thanks, Charlie. Yeah, simple questions, actually. I could ask these guys questions all afternoon, but I know it's cutting short. First one is dextrinization versus gelatinization. I have an issue with students. They read papers, they read books, and I feel like a lone maverick trying to convince them it's not gelatinization, it's dextrinization. Any other clues you can help me convince students when discussing the extrusion cooking process?
Time scale. That's it. Yeah. If anyone tells you they can gelatinize in 15 seconds, they're fooling themselves. True gelatinization requires lots of water, typically in excess of 60%, and lots of time.
Yeah, I've come to the conclusion, Dennis, to get this over, I've got to use your tricks. Before I start extrusion cooking, I get a pan and boil some eggs, and I get some porridge, and I make some porridge to try and demonstrate the process. A bit elementary, but you say you're fighting all the previous papers and written papers that says gelatinization. It's and so they think I'm a bit cranky and not particularly accurate.
This has been a long.
Unfortunately, a lot of food chemists don't differentiate the different ways it's cooked, and they just call it all gelatinization.
Yeah.
What we want to stress is that it is important. It does make a difference in real products, how it's cooked.
Yeah. Absolutely.
Okay. Yeah. So I'm boiling eggs now, guys, from your last lectures. Yeah.
Very good.
Did you have a second question?
Yeah, I did. Yeah, scale up is obviously is interesting for me because obviously I've just not to publicise it, but I don't know if you can see that. So thank you for the book about plant scale up. Can I just ask you, what are in your experiences, what are the main challenges on scale up? What is it you sort of, which is your top three that you sort of I've got to satisfy those three before I can go anywhere else on scale up?
First and foremost is really taking the time to understand what you're doing now. And most people don't. They just suddenly have a business decision that big orders come in. We need to go double the output, triple, tenfold, whatever. And we want it done next week. And they're not even 100% sure what they're doing today. That's made the marketplace respond the way it has. And so this is why a lot of scale-ups tend to fail, because not enough time is taken at the pilot plant to scale, to study and really understand everything that's going on. And what is the really, of that list of unit operations, which is the really critical one? You know, because there will be one or two that really determine what's going on in the product.
Okay. Yeah. Okay, that's good. Thank you.
My question really was, I mean, I'm obviously drawn to the mechanical side of it, but the screws are incredibly complex shapes, and presumably they're in food grade material. What sort of manufacturing processes do they use to make them?
About normal tooling, some depending on the material of construction. So there are some very expensive, high wear, ceramic impregnated materials and all this sort of stuff. But generally it's just normal machining technology. So most of these things are just cut on a lathe, and then if they do incorporate any specialty materials, usually there's just simple surface coatings on the screws themselves. Okay. Yeah.
Just in your written, you mentioned stainless steel. Generally, they're not stainless steel, so they are easier to machine.
So they tend to be coated. Coated, and
Okay. And then various heat treatments to get, depending on, because it depends on the specific application. The wear of the extruder could be corrosion related, abrasion. It depends on, so then there are specialty materials sometimes used, but typically just high-speed tool steels are what are used.
Okay. Yeah. Okay. Thank you. David White, you had a question?
I just need to. Oh yes, it was about the simulation. There was a slide where you showed what you might call mechanical simulation. I think it was Pro-T. I can't remember the exact name of the simulation you used. But from what you've said about the actual products and all the factors that influence the products, to actually then simulate what you're going to get at in terms of a product is probably at this stage very difficult or impossible, and the software can't cope with it.
Correct. And that's why there's a lot of published papers, showing lots of pretty pictures and animations such as those, but they are very hypothetical and very special, like this, this is water doing this in an extruder screw, or because as soon as you implement all the non-Newtonian mechanics on top of it, it becomes so complex that even supercomputers probably wouldn't handle it. But yet we expect lowly paid operators to deal with it every day. So that's always been my bugbear. The PhDs can't do it, but the old operator is supposed to.
And just coming back to that, there was actually thank you very much for that answer. There was, what was going through my mind was the operators.
Yeah.
And, if you get a line going down, it's gone down for half a day, there must be a temptation, and there must be plenty of examples where somebody's gone, well, we'll just slightly up the rate on this to get back onto schedule.
Correct. And then they end up going down the gurgler. And it's like one of the things Gordon mentioned at the beginning, you can't cook an egg twice. So a lot more often than not, when the process is running out of specification, product is being accumulated that is not acceptable, and people then try and sneak it back in. Oh, we'll just rework it. But you can't cook an egg twice. So what happens second time around? We make more rubbish. And so they start chasing their tails. And so, managing these processes can be quite challenging, especially because more often than not, most people have no idea what the hell's going on anyway.
Yeah, thank you very much.
Yep.
Yeah, it's incredible. I mean, obviously I've got a reasonable amount of experience in plastics and moldings and die castings and things in the mechanical world. It's so similar, high pressure die casting, and you are, at the end of the day, you're cooking material, aren't you?
Yes.
Yeah. Whether you're producing a plastic part or an extruded piece of aluminium or whatever. Yeah, it's fascinating. Okay, well, I don't think we've got any more questions unless anybody else has anything, so I should draw it to a close because it's just a little bit over. Well, thank you both to our presenters for working into the evening. I don't know what time it is there now, but ready for a beer.
Definitely.
Thanks for taking the time out to present. As a non-food engineer, I certainly found it incredibly interesting. It'll certainly make me think next time I'm eating cereal or stealing snacks off the kids. There was a question about the video. We will edit the video and it'll go onto our website and our YouTube channel in due course. If anybody on the call are not members of IAgrE and they're interested, then please visit the website. It's not expensive to join. We have a real good mix of content, as you've seen today. And we're also licensed to provide professional qualifications such as CEng to practicing engineers. So please keep a lookout for future events and we'll see you next time. Bye-bye.